welcome back to another example of recursion. And I said in this video that I was going to deal with arrays, but before I do arrays, there is an important recursion I want to show you that doesn't involve arrays, but it's actually very, very useful in outputting numbers. And basically the code I'm showing you here is code that has been used throughout the years in operating systems to print out numbers. Okay, and so let's take a look at what we're trying to do. Here's my little main method that I put right next to the code, so I don't have to keep moving things around. In fact, let me just go ahead and make this bigger. And what I want to do is take this number and print it out to the screen base 10. Well, printing out that number base 10 is basically 1, 2, 3, 4, 5, because that's base 10. But the algorithm I'm going to show you here really doesn't matter that it's base 10. It could be base 8, it could be base 2. We're going to explain that. We're going to see that that will work the same. By doing base 2 is binary, and that 1, 2, 3, 4, 5 is going to be output in binary. So any base you want, it doesn't really matter. It's just easier to understand the algorithm with base 10 because we're used to base 10. So what's going on here? Well, what goes on here is we call this method, and that's sort of the public method that people use, and it starts to recursion. See, the special case is if x is equal to 0. If x is equal to 0, x really doesn't have any real digits. It's got no value, so I'm just going to output the 0 there. Okay. Otherwise, we've got digits to output. That's the way you interpret that. You've got digits to output, and so the way you interpret this binary helper, decimal to binary helper, is that you've got to believe that if I pass it a number, it's going to output that number to this base. So let's see how we do that. Go back up here. Decimal to binary helper, I pass it a number, I pass it a base, and to be really cute about this, listen, if x is less than 0, all right, we're going to output a little minus sign in front of this thing, and then we're going to call binary with the binary helper with a negative x. So the negative's already been taken care of. So if I had negative 1, 2, 3, 4, 5, I'm going to call that same method with 1, 2, 3, 4, 5. And as long as there's digits to output, that's the way you interpret that, x being 1, 2, 3, 4, 5, I've got something to do. So how do I output that 5-digit number? Here's how you do it. You've got to believe that this is going to output this value correctly. What am I doing here? I'm taking 1, 2, 3, 4, 5, dividing it by 10. Now 1, 2, 3, 4, 5 divided by 10 is 1, 2, 3, 4. So let's pretend, okay, that this works. X is 1, 2, 3, 4, 5. But what we have here is 1, 2, 3, 4 actually output to the screen. Okay? And then after we output the first leading digits, this is basically what we're saying. We're outputting the first leading digits of the number. Then if I take x mod base, 1, 2, 3, 4, 5 mod 10, it's going to output the 5. It's going to output the 5. So after we output the leading digits, we can just output the 5 when we outputted the string properly. Okay, now basically the base case here is if x is equal to 0, because if x is equal to 0, we do essentially nothing. And you might be saying, well, why don't I just say this? This out 0. And the reason I didn't do that is because I'm going to, if you look at the logic, I'd be always outputting a leading 0. I'd always be getting something like 0, 1, 2, 3, 4, 5, and that just doesn't look right. Okay, that just doesn't look right. So what I'm going to do is just take this code out. I've already worried about the special case of 0 here. So I'm not. So if I do input 0 to this method, I'm going to output the 0 and be done with it. But and the way you interpret, if else you've got some digits to output, I'll output the digits here. Okay, and it doesn't matter. Let's see if this works. The first line was 1, 2, 3, 4, 5, and you're going to say, well, geez. Okay, how do I know that works? Well, I can tell you how it works. This is the first line. And the second line is a little bit different. See, the problem with this first set of the basic logic is over here, is that I'm using a void method. And a void method doesn't return anything. I really would probably want to return the string that represents the value that I would like to output. And so I have another set of code right here with the word str, string decimal to base. And instead of outputting something, I'm going to return a string. And the logic is pretty much the same. If x is 0, I return the string 0. Otherwise, I'm going to return this string here. Now remember, 1, 2, 3, 4, 5. And you've got to believe that if that method's written correctly, that helper function is going to output string 1, 2, 3, 4, 5 to base 10. Let's go back here, show you how we're doing it. All right, so look, if x is less than 0, I return, this is just one big string with a minus sign in front. I'm going to call that same method again with a negative x, so a negative number becomes a positive, and we're going to output those digits. And then the next time you call this, string decimal to binary is going to be a positive number here, so x divided by base. Well, you got to believe the recursion is this. You got to believe that if I passed it x as 1, 2, 3, 4, 5, x divided by 10, the base is 1, 2, 3, 4. You've got to believe in what you're doing here, that this is going to return 1, 2, 3, 4, 5, no, excuse me, 1, 2, 3, 4 as a string. And once that's done, that comes back with 1, 2, 3, 4 string. What I'm going to do is concatenate. This is concatenation right here. I'm going to concatenate x mod base, which is the last digit of 1, 2, 3, 4, 5, which is 5. And it should work. And I think it did work because, actually, I think I might want to do this just to bring home the fact that we are returning string. String value of string value of, okay, I think I might want to do that just to bring home the idea that, see, this is a number, okay, because you're doing math on a number, and I'm converting that number to a string. That might be a little bit better. Now, if by any chance you pass it as 0, I'm going to return a null string. See, eventually, you're going to get to the point where, say you want to output 6, the number 6. 6 mod base is going to, 6 is bigger than 0, so you're going to say 6 mod base mod 10 divided by 10 is 0. What's going to happen, we do another recursive call, and we don't want to output a 0, we just want to output no digits, which is null. And then we come back to this level to output the 6. 6 mod 10 would be 6, and you output the variable 6. So here's the two cases here. We run this, 1, 2, 3, 4, 5, and just to show you that this logic, I can convert anything to any base for using this logic. Here's base 2. Okay, and you got to believe, just go online and find a binary to decimal calculator. I gotta believe that this sequence of 1s and 0s is 1, 2, 3, 4, 5. If you go online and pass it base 8, base 8, base 8, that's octal. You get that. Okay, so octal means every digit, 1/8 to the 0s times plus 7 times 8 to the first. 0 times 8 squared. 0 times 8 to the third power, 3 times 8 to the fourth power, all added up would give you 1, 2, 3, 4, 5. Now, logically, I could extend this to any base you want. The problem, however, is when you do remainders, with base 16, you need the letters A, B, C, D, and I didn't incorporate that logic in this code. I'll leave that up to you. Okay, you see, what the problem is, if you do base 16, something bigger than 10, you need 16 digits to represent the remainder. So base 16, this could give you a number between 0 and 15 inclusive, and you have to convert that number 10, 11, 12 into letters A, B, C, and that wasn't the point of this. So I'll leave that up to you to actually do that logic. Okay, we'll see you in the next video.